Hello, everyone. So, our today topic of discussion is oxidation of aldehyde. We have talked about the other reactions of aldehyde, and we have seen in the previous lecture the keto-enol tautomerism, an aldehyde and the ketones one. And today I will, though the topic is the oxidation of aldehyde and ketones, but I am just discussing the oxidation of aldehyde in today's lecture. So we will cover the oxidation of ketones and other reactions in the future lectures. So for today's lecture, I am using my handwritten pages because some of the students requested for the style too. So that would be the comparison, and you can comment on it. Either you are more comfortable with the slides, and you are more comfortable with my handwritten handouts screens. So we will talk about the oxidation of aldehyde. So what you assume and what come into your mind when you're talking about that aldehyde is one functional group, and if we oxidize it, so what should be the functionality change from aldehyde to another functional group? So you can think about for a few time for a very short period, and maybe you get an answer, and even if you don't, so we can discuss it. So whenever we go for the oxidation of aldehyde, so we can synthesize the carboxylic acid, or you can say the carboxylic acids. The one way to synthesize the carboxylic acid is the oxidation of aldehyde. An interesting thing about aldehyde is that they are one of the most easily oxidizable functional group among the all other organic uh, class of the functional groups or the class of the compounds. So there are a number of different ways. So if these are aldehydes are easily oxidizable, it means that we can use the normal or the common oxidizing agents for their oxidation. So I have listed the three common and ways, though there are a number of different reactions we can conduct and reagents we can use for the oxidation of aldehyde. But in our scope and discussion, I have picked these three, which we will cover in this this course. So the first one is the chromic acid. Another one is silver iron, and for the silver iron utilization, we can use the silver oxide as a source. The third one is the molecular oxygen and hydrogen peroxide. So in today's lecture, we are concentrating or we are limiting our discussion with these two. One is the oxidation of aldehyde with chromic acid, and the second one is the oxidation with silver iron or silver oxide. One more important thing I want you to keep in your mind, that the mechanism I'm going to discuss with you is not in your chapter 16, which we are following, the organic chemistry by Brown and Forte. So I am sharing and I'm discussing with you mechanism here in a lecture, and these handouts will be shared on Moodle for your lecture notes. So you have to follow the lecture notes, because for exam you can't take that excuse that this was not mentioned, the mechanism was not mentioned in a book. So I am providing you this mechanism, and we'll talk about the mechanism. So in that chapter, they have only discussed the different reactions of the oxidation of aldehyde by using these reagents. So firstly, we are going to discuss the first reaction, which is the oxidation of aldehyde by chromic acid. So here the overall reaction is just that when we are using any of the aldehyde and we are adding the chromic acid in it, so this functionality, which is the aldehyde, is converting into the carboxylic acid functionality. So now the hexanol, which is our starting material, is converting into hexanoic acid in the presence of chromic acid. So now we will discuss its mechanism. So for mechanism, I am writing the general kind of reaction. So firstly, there is a need that you understand the general reaction mechanism, and then you can change and you can practice with different aldehydes, and definitely you will generate their respective carboxylic acid, and the carboxylic acid will be the product, and it depends, our group depends that what are the starting aldehyde you are using. So the reaction condition, that how we are proceeding that reaction or how we conduct that reaction in our lab, is that here we will use the acidic aqueous solution of chromic acid, right? And because these aldehyde or most of the organic compounds are not soluble in aqueous medium, so for this we will use the acetone as a solvent. Acetone is an aprotic solvent, so we will use that one. So now starting with an aldehyde, this is a general aldehyde, that our group can be any chain, or that could be uh, the aromatic aryl group, that could be alkyl group, right? So this is the aqueous medium. So here, the very first step is a fast and reversible step. So this is constantly in an equilibrium. This is moving forward and backward, depending on that what are the concentrations of the starting material. So the first thing which is happening to this reaction is that this carbon and oxygen is rearranging, or it is taking back its pi electron. And because in a medium, this is the aqueous medium, and we have the hydroxyl ion supply, so that can attack on this electrophilic carbon, which will be electron deficient once the carbon and oxygen is taking back its electron, right? So now there's the this oxygen is hydrated with this H positive, and this hydroxyl ion is attacking, or this has attached with that electron deficient or electrophilic carbon. Now this is the OH, this is OH, and this is the H, which was initially attached with this aldehyde group, right? Now there is a chromic acid, H2CrO4. So what happened when we add the chromic acid here? The chromic acid we are using is in a solution format. This is the acidic solution, and for the acidic medium we use the sulfuric acid, or even HCl can also be used for the acidification or the workup of that reaction. So now what is happening, and the only participating reagent is basically the H2CrO4, which is the most important one, though these are hydroxyl or aqueous medium is using for the internal rearrangement and then hydration and some of the intermediate steps, right? So the major intermediate will be formed when we are reacting it with the chromic acid, because this is applying the extra oxygen by which that is converting into the carboxylic acid. So here, this is the hydrated form of the aldehyde. Now, the chromic acid we are adding, this is the liver structure of chromic acid. So chromium is in oxidation state 6. This is making 6 bond, 2 doubly bonded with the oxygen. Then there is one with the hydroxyl, and there is one with the hydroxyl. On both sides, there is a hydroxyl group. So now what is happening to the chromium, and what are the different adjustment or the electron movement, which will be shown by the curly arrows, that how that reaction is proceeding. So from the chromium oxide, this bond of oxygen and hydrogen will be broken. So that electron pair will go back to this oxygen, right? Now this carbon and oxygen bond will be broken, right? And that hydroxyl could be of any side, you can choose here. So now this is taking back its electron. So this bond will be break, right? And this hydrogen, because this has removed from the oxygen, they will combine and that will convert into the water molecule. So there is the first thing is there is the water elimination, right? So here I have mentioned this H3O hydronium ion because there is the acidic solution, so there is the extra hydrogen ion there. Now the next thing is that now this carbon is getting electron deficient because this fourth bond of oxygen and carbon has broken. Now this chromium oxide from this oxygen, which is a nucleophile, will attack on this electrophilic carbon. Now, what would be the form of that intermediate? R, C, H, OH, and this chromate has attached to that side, right? So now this is the intermediate, and we know that this reaction is happening in the aqueous medium. So this is present in a system, right? So when this water is um, in contact with this chromate of the aldehyde one, right? So now this is in an alcoholic form that aldehyde has converted into the alcoholic functionality, and there is the chromate which is attached to this. Now this water molecule is approaching this, so this is taking up that hydrogen through this oxygen, and that bond will be broken. So there will be the double bond. So once this oxygen is in a double bond with the carbon, so definitely there is no point for this extra bond, because then oxygen will get in a positive um, charge, which is not the stable form, right? So this is breaking that bond, and here this is the R, C double bond O, and this is the OH, right? So this is a carboxylic acid, and we left with the CrO3H, right, and negative, and there is the H3O positive. So this is the reaction mechanism, how the aldehyde oxidize into their respective carboxylic acid in the presence of chromic acid. One important thing is that how we can have that chromic acid, what are the different means or sources of the chromic acid, so that chromic acid can be produced by the reaction of chromium oxide with the water by adding the sulfuric acid. So we will have the chromic acid. The other way, the other source is potassium dichromate, and if we mix it with the hydrogen sulfide, sulfuric acid, so then we will get this H2Cr2O7, which on the interaction with the water, this will convert into the chromic acid, right? So you may have used the chromic acid for the washing of your glassware in lab. So how we prepare this, that we use to take the potassium dichromate, and we put its solution in the saturated solution and the sulfuric acid, and then that reagent is used for the washing of the glassware, when especially when we are using these glassware for the stock solution for the spectroscopic analysis, where the elemental analysis is required. So the glassware should be uh, from any of the impurity. So another term which you should remember is this reaction has happened in the acidic aqueous solution of the chromic acid, and that mixture is called John's reagent. So you should not be confused if someone asking you that what would be the product if the aldehyde is reacted in with the John's reagent. So you should know that John's reagent means that there is a chromic acid in aqueous sulfuric acid, and that is termed as John's reagent. So that was our first oxidation method for the aldehyde one. Now we will switch to the next one. This is a very common but very famous, but maybe we usually, and we very commonly perform in our biochemistry lab. This is a Tollen's reagent test, or this is very commonly familiar, famous with the silver mirror test. You may have discussed in organic chemistry, um, a little bit in the uh, respect of experimental lab. But now we will see that what is the mechanism and how the aldehyde, we can distinguish between the aldehydic carbohydrates and the ketonic carbohydrates on the basis of these Tollen's reagent. So that Tollen's reagent or a silver mirror test is the distinction or differentiation test between the aldehyde and the ketone one. So always the aldehyde will give this test positive. So we will get the reaction flask silvery like the mirror. Um, so that will be the silver glossy, because there is a metallic silver which deposited, and that test will be positive in case of the aldehyde, but the ketones will give this test negative. So now we'll see that what happened in this test. So this is basically the alkaline solution of the silver um, nitrate we use, or the silver oxide. So the solution of silver oxide is used as a source of the silver. So initially there was the reagent which will use the silver nitrate, but that is very expensive. So now there are the air oxidations is another way for the oxidation of aldehyde for using it, but still for the mirroring of the glass, this test is still in use. So now what is happening in this, that this is the silver which we use any of the salt of the silver, and we pass through the ammonia, and there is an aqueous solution of it. So then we convert this silver into the metallic one, and there is ammonia. When this aldehyde and the basic medium react there, so this is basically giving that electron to the system, because the carbohydrates are the reducing sugars. So they do oxidized uh, the metal, right? And then they reduce the metal and they oxidize by themselves. So we will see that what is happening to the aldehydes there. So here, this is the aldehyde, and there is a removal of electron from this carbon and oxygen, right? And this Ag positive, because I have stated firstly that this reaction is specific for the silver one oxidation state. So silver plus one will convert into its silver zero, means this has taken up the electron. So this get reduced. This is a reducing agent, but this will be oxidized, and later you will see in this reaction. So now this is the O radical. There is a single electron, because single electron has removed from these valence electrons. So now this carbon and this double bond has broken. So this carbon is get electropositive, and here is the OH which is supplied by the alkaline medium. We are using sodium hydroxide there. So now this will attack on this electrophilic carbon center, and here this oxygen is the O radical, right? There is R, there is H, and this is the OH which get attached on this carbon. Now the next change to this intermediate is that this will rearrange for its stable form, because this O radical is very reactive and it has to go for and this oxygen radical anion is not as stable as we can go for the carbon anion, right? So now this will convert into the intermediate where we have the carbon anion radical. So here this OH, which is in a system, right? So that has rearranged itself in the form, this is the O negative because that bond has broken, right? And R, this is radical, and this is the OH1. Now this electron will remove from this system, and this will be accepted by the silver plus, which is in the system because we are using the stoichiometric amount of that silver salt, which is continuously supplying the Ag positive one, which get reduced into the metallic silver. So now this is the R, and this negative will form the double bond here, right? And this is the carbonyl, and there is the hydroxyl one. This hydroxyl can remove from this. So this is the hydration or the reduction. So you can have this. Uh, Basically, the point is this one, that usually I have written this carboxylic acid, but what actually happened, that this is the form which formed here. This is a carboxylate salt, and then if there are the H positive in the system which are present in this reaction, so they get hydrated and there is the carboxylic acid. Or otherwise you can just go for straightly for this end product, if that is confusing to do, but you should know the concept of it. So basically that negative means there is the electron pair that move here, and this is establishing the double bond with the carbon, right? And this extra radical electron has removed from that system. So now the product is the carboxylic acid. So we can use the different aldehydes and we will get the respective carboxylic acids of that aldehyde. Now at the end, I have a task for you, so that you have to submit on the Moodle, and I will give you the 2 day probably for this. So I have given you the starting material, and I have mentioned the condition also that we are using the Tollen's reagent. So Tollen's reagent means that this is a sodium hydroxide, there is a water medium, this is a acidic solution, and there is the silver salt, right? We are using here, and what would be the product of it? So definitely the oxidation of the aldehyde results in the carboxylic acid, but you have to write the mechanism, you have to give the proper structure of that carboxylic acid, because this is not the general equation, this is not the general reaction. I have specified this aldehyde, which is the 3-phenyl propanol. So now you have to write its IUPAC name too. So I hope you get that concept that how this oxidation is proceeding. But if you have any questions, you can write to me and we can discuss this. Thank you. Have a good day.